In this exercise we consider a buoy, an underwater buoy, which corresponds to a cube, and this cube is immersed inside the water as represented in this figure. So here we have the surface of the water. In the left, the cube or the buoy is totally immersed. Here it is at the surface and the depth is equal to 0. So to consider the depth, we consider the top of the cube or of the buoy. And here the depth is negative because the top of the buoy is above the water. L is the size of the cube. So in this cube there is a ballast with a pump, volume, changing volume. We change the density of the cube, and due to this ballast, the force exerted in the cube depends on the gravity, as represented here, but also the Archimedes Force, written here. We'll see why later it is this, and also a friction force, which tells us that when the cube is moving with a speed v, then there is some friction force that will slow down the motion of the cube. So Fj is a gravity force, Fd is a drag force, and Fa is the Archimedes force. The buoy is represented here, which corresponds to a cube. The size of the cube is L, and we have an antenna. The volume is considered to be equal to 0. That will help us to communicate with the buoy, but we'll not take it into account here. We'll have a two-dimensional view of the cube will be represented like this, and D corresponds to this distance. So in this situation, the buoy is at the surface and D corresponds to 0, but D can be negative like this. In the simulation, I will represent the buoy as follows. As here we have the antenna, we have the cube, and here we have an empty volume, so which is air inside, which makes it possible to control the density of the buoy. So it will correspond to the variable b, and there is a DC motor that can change this volume. When b equal to 0, like it is in this picture, it means that the buoyancy of the buoy is neither positive nor negative, so b corresponds to the buoyancy, and the buoy will stay at the same position. When b is positive, then the density will be larger of the buoy will be larger than that of the water, and L will go downward, so downward. When b is negative, the buoyancy will be oriented upward. The density will be smaller than that of the water, and the buoy will go upward. So we can control this volume thanks to a variable u, and in fact we'll have the derivative of b is equal to u. So thanks to the physical reasons, we'll assume that u belongs to -1, 1, and the volume is also limited, so the volume b also belongs to -1, 1. What we can say that the density ρ of the water is ρ0, so water. But the density ρ of the buoy is not exactly equal to that of the water. It corresponds to 1 plus some coefficient, 0.1 for instance, multiplied by b, multiplied by ρ0. So this coefficient can call it beta, for instance. It depends of the boy. But it means that rho is almost equal to rho 0. But if b equal to 0, as said here, then rho equal to rho 0. That's why the boy does not change. But we can see that if it is positive, then I will go downward, and negative, I will go upward. So now what I have to do is to write the state equation of this system. So the state variable are first the depth, d, the derivative. So since we are under the water, we need to orient it like this. D is oriented like this. So 0, and here positive, and in this direction negative. So d is the first state variable, so x corresponds to d. The speed, let's say like this, v, and also the volume, represented here, the volume that we can control. So I will add here this volume, I have called it b. Now I have to write the state equation. So I have to write something like d dot equal v dot equal b dot equal. And to have state equation, here I need to write only as variables d, v, b, and of course u. In this case, I will have something like x dot equal f of x and u, and u, and I will be able to simulate it. So first, I have d dot equal to v, I have b dot equal to u, and now I will have to find what I have to write here. So to do this, I will use the Newton second rule, which tells me that mv dot equal to the sum of all forces. So for the forces, I will have the weight. So I will have the force corresponding to the weight. So the weight will go downward. So that's right, I will put plus. So this one in this direction. Here I will have minus the Archimedes Force, Fa, which will move the boy upward. And also I will have the friction force. I will put a minus also, which corresponds the drag force, F. I will write Ft. So this one move upward, and this one it can move downward or upward, depending of the direction of the motion of the boy. For the gravity force, so Fj, I will have, of course, m times j. For the drag force, it will be 1/2 times the density of the water multiplied by v square. So v square, but I have the sign, so I will write vw, and the absolute value of v times the surface. So the surface of the cube will be L times 2, and Cx depend of the shape. So for a cube, so I write a cube like this. the surface like this corresponds to L square, and due to the shape which is not hydrodynamical for the cube, I have a Cx corresponding to something like 1.05. But if I would have a buoy like this, for instance, like a torpedo, like this, for instance, then Cx would be much smaller. For instance, something like 0.2, 0.3, because it can move much more easily up and down thanks to its shape. I will write a minus also. Okay, there is a minus because when I move downward, so in the positive direction, when V is positive, then Fd is Fd in this direction. So the drag is in the opposite direction. That's why here I have a minus. Now the last one corresponds to the Archimedes Force. So the Archimedes Force, the force that is exerted upward, so like this, Fa, and it depends, it is proportional to the volume of the body that is immersed. So in this situation, the volume corresponds to L cube. But in this situation, it will be different because only this part of the volume is immersed, and in this case, D is negative. So here, D is equal to 0, because here I am just at the surface of the water, and here D corresponds to minus L. So in this situation or this situation, it will correspond to the same. So in this situation and this situation also. So if we want to represent like this, the force, if I have minus L like this, and here I will have 0. So I can represent the immersed volume. So immersed volume like this. When D is positive, I have something equal to L square. When I am in this situation or this situation like this, I will have 0, and here I will have a function like this. So that's why the immersed volume will correspond to L2 times the immersed size, if you want, which corresponds to the maximum. So I am now writing this function, maximum of 0 L plus minimum of D and 0. So let me explain this. First, if I consider the situation where D is positive, for instance, D is positive. In this situation, the minimum will correspond to 0. So in this case, I will have L. The max of 0 and L will be L, and then here I will have L cube, which is normal, as I have explained here. Now, I will consider the situation where D is below than minus L. So for instance, when I am here, for instance. So in this situation, D corresponds to minus L, so this will be minus L. L minus L will correspond to 0. The maximum will be 0. L squared times 0 will correspond to 0, which is consistent to what I have written here. And if I am between minus L and L, we can easily understand that it will correspond to L. That's why it is consistent with what I have written here. So now I have a knowledge of all these forces. I can isolate V, and I can write that V is equal to 1 divided, so V dot, excuse me, here V dot, yes, V dot correspond to 1 times, so the gravity, mj minus rho 0 gl square multiplied by max of 0 L plus min of d0, as explained just above, minus 1/2 v square cx. Now we know that the mass is equal to 1 plus beta b multiplied by rho 0, so it corresponds to the density of the buoy multiplied by the volume L square. So recall that I can control this volume thanks to U. So of course I have some simplification between L square, L3, and I obtain this state equation written here. So it corresponds to something like x dot equal f of x and u, and I will be able to simulate this. After, of course, I will have to control to go at a given depth. I take a Python program written here where I have a function to draw the buoy. Here I start with an initial state vector, which tells me that the buoy is at a depth equal to 3. The speed is 0, and the volume, the control volume, is equal to 0 also. So that's why the buoy will neither go upward or downward. And then I show to what corresponds this program. I have it here. So the buoy, it's at -3, so 3, the depth is 3. We can see the antenna, and here's the empty volume, which is half. It means that I will neither go upward nor downward. So I can, of course, more if I add more water, more I will go, more the density will be high, and I will sink. So we can see on the volume, if I put here the maximum, which corresponds to 1, then we can see here that it is full of water. And when I put -1, the maximum, then we can see that it is empty. For the simulation, I will have to add a loop here for t in arrange. So I will start at 0 and let's say for 10 seconds dt. So dt is a small number. I will initialize dt equal to say 0.05, for instance. The loop will be a layer loop, so the new x corresponds to the old one plus dt multiplied by f of x and u. So it is a Euler method I use for the integration. I will have to add the evolution function, which is given here. So dvb corresponds to the depth, velocity and buoyancy. So first I flatten the vector so that I can obtain x of 0 and x of 1 easily, and I initialize the depth, velocity and buoyancy variable thanks to the states. Rho is initialized to 1000 because it is the density of the water. It may correspond to rho 0. J 9.A1 classical, and for the cube the Cx is 1.05. And V dot, as explained thanks to the Newton law, we have obtained that it is given here, and I return V, dv and u, as explained before. Here I have to put this and to initialize u, for instance, to 0. It means that I don't change the volume of the ballast. I run this, and we can see here the buoy moving upward, normal, and oscillate at the surface, which is normal. The entity is empty, so the buoyancy is positive, and the buoys go upward, and I see some simulation after. So the simulation has finished. Here, to understand this, if I will try to change some coefficient. So if here I initialize to +1, then we will see that the buoys is sinking. Okay, goes downward. So I will try to understand better this formula. Well, okay, I will put 0 at the moment, so the buoyancy corresponds to 0, and normally it should not change. Okay, that's why we understand it is not moving, because empty volume is half of the volume as represented in the picture. Now I will try to change this formula to have a better understanding. If I put only the gravity, so it means that I have only the gravity force, so no Archimedes force and no friction with the water, and we will see that it goes down and it accelerates like if I am in the empty space. Okay, which is rather normal. Now if I only add the friction, then of course I will go down, but quickly I will represent it here. Yes, if I put like this, then we'll see that it goes down, but due to a minus. Okay, yes, we can see that it is slowed down thanks to the friction. And now, of course, due to the Archimedes force, I have this will influence, due to the buoyancy, will influence, and I can now move upward. Question number 2. I assume that the buoy is now totally immersed, and I have to find a sliding mode controller so that the buoy goes at the depth d, which corresponds to the desired depth, denoted by d0. So that's why I have to do now. So the depth should be equal to the one I want, and this one can move with respect to time. So since we use a sliding mode controller, we'll need the derivative of the depth in order to be able to converge to the desired depth. Here are the state equation of the buoy. When the buoy is immerged, totally immerged, D is positive. So the mean of D and 0 corresponds to 0. So this eliminates. And the max of 0 and a positive number is this positive number. So this corresponds to L. And I obtain this state equation. So the simplification is given here. To use a sliding mode controller, though, so recall that this is my system to be controlled if the buoy is immersed. This is U. And to use a sliding mode controller, I should choose an output to be controlled. So Y corresponds to the depth, D. And I have to compute the first derivative, Y dot, and Y dot. So 3 times. Now, the first one is D. The second one is D dot, which corresponds to V. Oh, I have this here. And the last one, so Y dot corresponds to V dot, which is equal to J minus JL plus 1/2 V square CX divided by 1 plus beta B times L. Okay. And I do not need to compute this quantity. So why? Because in this particular case, we can see that there is some monotonicity of Y dot dot with respect to B. So if I increase B, then Y dot dot will increase. So I don't need this quantity, and this will help me to simplify the reasoning. So now I have to choose a surface. So the surface I will choose S of X and T. So the surface, a sliding mode surface, where X is a state. So recall that T corresponds to D, V, and B. Okay. This surface I will choose will be the following. So Y dot D, so the derivative, the second derivative of the desired depth, minus Y dot plus let's say 2. I will explain this just after. Y dot 1 minus D minus Y D plus Y D minus Y. And this surface should be equal to 0. So let me explain why I have chosen this, because if this corresponds to the derivative of the error, the second derivative, first order derivative, first order E dot, here is E, then I obtain an equation Y dot plus 2Y dot plus E equals to 0, and this is stable. So it means that the limit of E of t is equal to 0 when t go to infinity. And the constant, associated constant, is something like t equal 1 second. So now I know that this quantity, so I know this quantity. Since I know what I want, I know yd, an expression, a temporal expression of yd. So I need this quantity, and this quantity. I know also that y corresponds to the depth d. This one corresponds to v. And this one corresponds to this quantity. Okay. So in fact, I have a surface which depends on d, v, and b, because I have the expression here where v, d, and so on appears. And if I draw a picture of this surface, I will have something like this. So here it may correspond to d, for instance, here to v, here to b, and there, excuse me, I have a surface here. I draw it like this, two-dimensional surface, which corresponds to s of x and t equals 0. So this surface is moving. But as soon as I am on this surface, then I will stay on. If I am able to stay on this surface, then I will move and converge, I don't know how, to one point which corresponds to an error which is equal to 0. Consider the case where s is positive. So recall that here on the surface it is negative, in one side it is positive, and on the other side s is negative. So assume that s is positive. So it means that what I want to do is to decrease. I want to decrease s so that it will go to 0. Now, since I have a minus here, I have to increase y dot. So thus, I want y dot to increase because of the minus. Now, due to the state equation, here, since here I have y dot dot, I can influence b in order to increase y dot dot. So I will take b, since y dot dot is increasing with respect to b. The objective is to have b as high as possible. So it means, because I have minus in the denominator, so it compensates, and there is, when I increase b, I increase y dot dot. So it means that I have to increase b. And in order to do this, I have to take u, the input, as high as possible. So u will be equal to u max, which in the exercise corresponds to 1. So in fact, when it is negative, s is negative, then of course I should take u is equal to minus 1. So it is the best what I can do. It is a principle of sliding mode control. So that's why I will take a u corresponds to the sign of s, where s is given here. I will put a line here to draw the desired depth. The desired depth will put here, let's say, to 5 meters. I will put the controller here, where d, v, and b are extracted from x. Then this is the sliding mode controller I have put just before. I need the derivative d0 dot so u will correspond to this. And if I want to go to a constant depth, I have to initialize d0 dot to 0 and d0 twice derivative to 0. Since in the controller I need some constants that such as j, I will extract from this function these values in order to put as global values here. I run the program and I see that I converge to -5 exactly, and I have no overshoot. I mean, I never go further the desired depth. The last step of the exercise is to replace this by some sine function. In the exercise, it is required that d0 corresponds to 3 plus sine t divided by 2. This is why here I have put the required depth and also the derivative here and double derivative here. If I run the program, I can see that I converge to the right depth, but also I can see that the control anticipates. So it knows the water come inside because it guesses from the derivative that it will have to go down. So there is some anticipation that are possible thanks to the derivative of the desired depth that are known by the controller.